Hello everyone. Am I audible to everybody? Am I audible to everybody? Please let me know. Okay. So let's start today's session. So in this session we are going to discuss about the RE model. In the previous lecture what we have done, we have discussed about the hybrid parameter model, and in today's lecture we are going to start a new type of modeling, that is more generalized modeling of the transistor, that is called the RE model. So using this RE model, we will again model the bipolar junction transistor, and this is the most generalized model that is used for modeling the bipolar junction transistor. And this modeling is quite similar to that of the hybrid parameter model. So first of all, we go for a circuit, and this circuit was a question of the Macaut examination. So let us first go for the circuit. So first circuit is again is the common emitter mode circuit with RE with RE, that is there will be a common emitter bipolar junction transistor with emitter resistance. So now hopefully you remember the circuit kya tha? The circuit was this is the transistor, this was the transistor, and this is the emitter region. So this is the emitter terminal, this is the collector terminal, and this is the base terminal. So this was the transistor. Since it is common emitter with RE, so there will be a emitter resistance at the emitter terminal and it will be grounded. So this is the RE resistor. Okay, and there will be a RC resistor, that is the collector resistor, that is connected to the collector terminal, and there will be a DC supply VCC. Similarly, at the base terminal, we will have a voltage AC signal, and the source resistance is denoted by RS, and there will be a AC signal source. So this is a AC signal source, and this AC signal source will be amplified by this amplifier, and the amplified output we will get from the collector. And here also we will apply a capacitor, and this type of capacitor, this is the coupling capacitor. We have already discussed about this in the previous lecture, and there is a load resistance here. So this is the load resistance RL, and here we will get the output voltage. So this is the capacitor, and there will also be a bypass capacitor, and this is called the bypass capacitor or emitter capacitor. So let us denote it with as CE. So this is the complete circuit of a common emitter mode with emitter resistance. With emitter resistance, this is the common emitter mode circuit. Now using this common emitter mode with RE resistor, we will try to model this circuit using the RE model. So first of all, in this case, if we denote the transistor, so where is the transistor? The transistor is here. This is the transistor, and this transistor will be replaced by the RE model. And in this transistor, we can see that the input current is IB, because now RE model, we use the RE model in the case of AC analysis. In the case of AC analysis, what we will do? We will make the VCC ground and we will make the capacitors. So capacitors means the reactance of the capacitor is equals to XC, and that is equals to 1 by omega C. And for AC analysis, we take the omega is very high. So if omega is very high, so XC will be very low. So that means the capacitors will be short circuited. So all the capacitors will be short circuited. So this capacitor will be short circuited for AC analysis, and this capacitor will also be short circuited for the AC analysis, and the VCC will also be 0. That means the VCC terminal will be grounded for the AC analysis. Now, the first thing, we have to replace this transistor using the RE model. And according to the RE model, so we can see that in the RE model, what will happen? So it will be similar to the hybrid parameter model. So here you can see the common terminal is the emitter. So common terminal is the emitter. So this is the common terminal, emitter. So this is the emitter terminal, and the base terminal is here, and here it is the collector terminal, output. So now in the RE model, what will happen? In the input circuit, there will be an input resistor that is called as R pi. So this is the R pi resistance, and the voltage across this R pi will be called as V pi. We are talking about the RE model. Similarly, in the output, there will be a dependent current source, and the value of the dependent current source is denoted by Gm into V pi. And there will be an admittance value, and the admittance value will be R pi. So this is R0. So this is R0. Now, in the circuit, you can see that this is a NPN transistor. So IE current will be in the outside direction. So IC will be in the incoming direction. So that means here we can replace that there is the base current and this is the collector current. And all are AC current because we are doing the AC analysis. Now this is the transistor. Now with the transistor, we have to connect the external circuits, that is RC, RL, RE, VS, RS, all these are external circuits. So now we want to connect the external parameters, that is the RC, RL, all these elements, external elements. So now you can see that collector is connected by RC to the ground. So that means this is the ground, and emitter terminal is connected to ground directly by the short circuit CE capacitor. So that means this terminal is grounded. Now collector terminal is also grounded by RC. So collector terminal will also be grounded by RC. So this is the RC. Okay, you can see. So this is the RC terminal. RC is connected. RC will be grounded to the by collector terminal. Now again also the collector terminal will also be grounded through RL. So there will be RL also. So there will be RL also. Okay. So across RL we are getting the output voltage. So this voltage is the V0 voltage. Okay. So now similarly at the input circuit, what is happening? Base is connected to the RS and RS through VS. So that means there is a RS and there is a VS. This is the input signal VS. So this is VS, this is RS. So this is the total RE model or AC model of the given circuit. Now here we can see there are different parameters. First one, if we talk about the internal parameters of the transistor. So internal parameters. So internal parameters means the parameters of the bipolar junction transistor. So what are the internal parameters? Here you can see R pi, V pi, GM. So R pi, V pi and GM are the internal parameters. We will discuss this. What is R pi, what is VM, what is GM. Okay. So parameters of BJT. Now, if we want to talk about the parameters that we have seen previously for a BJT, so we are calling that as the parameter for bipolar junction transistor. So bipolar junction transistors will have the parameters that we have already discussed in the previous lectures, that is the input resistance, the output resistance, the voltage gain and the current gain. Okay. Similarly, we will also have some parameters for the total circuits. For total circuit. So if we have parameter for total circuit, then it will be Ri dash, R0 dash and AVS and AV0. So AVS and AIS, current gain and the voltage gain of the total circuit. So it will be AIS. So these are the different parameters that we have to find. Now, if you remember, what is voltage gain? What was voltage gain? So voltage gain of the transistor, matlab parameters of the BJT. So parameters of the BJT, what was that? Parameters of BJT was voltage gain, current gain, input impedance and the output impedance of the BJT. Now, if we talk about the voltage gain of the BJT, what will be that? It will be the output voltage divided by input voltage. So, this is the BJT part. This is the BJT part. So, this part will have the output voltage, this one, and this voltage is similar to the output voltage V0. So, here it is V0. Okay. Now, this is the input voltage of the BJT. So this is the input voltage of the BJT and this Vi is equals to V pi. So we can say that V0 divided by Vi, which can be written as V0 divided by V pi. Okay, so this is the voltage gain. Similarly, if I want to find the voltage gain of the total circuit, that is AVS, this is total circuit. So it will also be V0 divided by the input voltage, and input voltage of the total circuit is Vs. So V0 by Vs is the voltage gain of the total circuit. Similarly, if we talk about the current gain of the BJT. So current gain of the BJT is nothing but output current. What is output current of BJT? That is IC, but the current must be flowing in the outward directions and we have positioned the current in the inward direction IC. So that means it will be minus IC divided by IB. But if we want to find the total current gain of the circuit, so total current gain of the circuit will be I0. Where is I0? I0 is the current flowing through the load resistance. And what is input current? Input current is the current flowing from the source. So that is I input. So that means I0 by I input. Now this I input is nothing but the IB. So I0 divided by IB. And what is I0 here? So we can find that I can find the I0 from the IC. Later on we will find that. So this is the thing that you have to think. So the value of the R pi, GM and R0. Okay. So the value of the R pi, GM, V pi, and there is another parameter also there. So that is R0. So GM value, the R pi value and the R0 value. These three parameter value do not change with the configuration. They will be similar for any configuration. For any type of, for a particular BJT, the value of GM, R pi, R0 will be same whether you connected the BJT for common emitter mode. If you connect the BJT for the common collector mode, then also the GM, R pi value and R0 value will be same. So now what we have to find some internal parameters of the BJT. So the first internal parameter is the R0 parameter. So now first we will have to discuss the internal output impedance. So what is the first parameter? The first parameter will be the internal output impedance of BJT. Okay, so this is the first parameter. Now this is denoted by small r0, and this small r0 is nothing but VA divided by IC. So that means if we want to calculate the internal impedance of a bipolar junction transistor, which is equals to R0, you have to find the value of VA, we have to find the value of DC collector current. So what is VA? VA is nothing but the early voltage. The early voltage. And this voltage value is very, very high value. Practically the value of the early voltage is very, very high. And this early voltage value is given in the data sheet. Every transistor has its own data sheet. And from that data sheet, we can find the value of early voltage. Generally, the value of the early voltage comes in between 50 to 100 volts. So graphically, if we want to find the VA, how can we find? For that, we have to recall the output characteristics of the bipolar junction transistor. Hopefully you remember the output characteristics of bipolar junction transistor. So it will be VCE versus the collector current. And if you remember the term, if you remember the graph, it looks like this. Similarly, there will be a curve looking like this, there will be a curve looking like this, and there will be a curve looking like this. Okay, so now if we extend the curve, if you extend this axis in the negative axis, and if we draw or extend this curve in the backward direction, so all this curve will meet at a point. All this extended curve will meet at one point. Okay, and this point is the value of VA. So this is the value this is the process by which we can find the early voltage of any transistor from the output characteristics. Now in the examination, what happens if VA is provided? If VA is provided, then we can take the value of VA which is provided, and if the VA is not provided, sometimes VA is also not provided in the examination. So if VA is not provided, that means if it is not provided in the numerical, then we will take the VA as infinite value, because VA will have a very, very high value. If VA is infinite, so the output impedance value will also be infinite. And what is this IC? This IC is nothing but the DC collector current. So that means for finding the IC, we have to do the DC analysis. So DC analysis By DC analysis, we will find the IC, and from the early voltage value, we will find the VA. We will make the ratio of VA by IC and take mod, and we will find the R0. So this is the process by which we can find the internal output impedance of a bipolar junction transistor. Similarly, the second parameter that you have to find or you have to understand, that is GM. So GM is called the transconductance of the bipolar junction transistor. So now what is GM? GM is denoted by mod of del I out. So the output current divided by del V in, and output current unit is milliampere and per volt. Sometimes in the case of MOSFETs, we get microampere divided by volt. And GM is also referred as the figure of merit. This is also called as figure of merit of the device or the MOSFETs. And GM generally signifies the sensitivity of the bipolar junction transistor. And GM is the most important parameter for the DC analysis or the RE model. AC analysis or the RE model. So you can see that the transconductance value is nothing but the output change in the output current divided by the change in the input voltage. Now we know that the IE current, IE is the output current. So IE is equals to IC. IE will be equals to IC, that is equals to I0 and e to the power VBE divided by VT minus 1. Okay, so now from this we can find the value of del IC divided by del of VBE. Okay, so now this is the GM, and if we do the partial derivative, we will get I0 e to the power VBE by VT divided by VT. Okay, so now this is the GM. Now from this we can write it as IC plus I0 divided by VT. Now we also know that the IC value is very much greater than I0, because IC will be in the milliamperes and I0 will be in the microamperes. So we can neglect the value of I0 with respect to IC, so it will be approximately equals to IC divided by VT. Okay, so this is IC divided by VT. So GM value comes to the value at IC divided by VT. So this is the value of the transconductance of the bipolar junction transistor, and this value will be needed in the case of RE model. And this GM value is always generally positive because there is a mod here, so there will be a mod here, so there will be a mod here, and there will be a mod here, so we can say IC, mod of IC. So GM value will be always positive. And what is the value of VT? VT is called as the thermal voltage. Thermal voltage. And the thermal voltage value can be determined from the equation capital T 11600, and T must be in the Kelvin. Generally for normal temperature, the thermal voltage value is 26 millivolt. Normal temperature means 27 degrees centigrade or 300 degree Kelvin. So this is the normal. So if we want to find the value of GM, so what we need to do? First we need to find the VT, and Vt can be found from the equation this according to the temperature value of the bipolar junction transistor, and the IC will be the DC current value. So DC collector current value should be determined from the DC analysis, and we'll make a ratio of the value with Vt. It will give the value of the transconductance. Transconductance value will be given by this. Now, if we go for the next case, that is, let us take some example. So if we take one example like this, if suppose we have found that after the DC analysis, we have found that the collector current value DC value is 1 milliampere, and the thermal voltage value is suppose 25 millivolt. So from this we can find the value of transconductance of the bipolar junction transistor, which is nothing but the mod of IC divided by Vt. Mod of IC means 1 milliampere divided by Vt means 25 millivolt. So this is the value of the GM, and we know the GM value will be expressed by milliampere per volt. So it will be 40 milliampere per volt. So this is how we can find the value of GM. Now the next parameter that we should discuss, that is the third parameter. It is the internal input impedance. Internal input impedance of bipolar junction transistor, and this internal input impedance is denoted by the R pi value. So how to find the R pi? R pi is found from beta AC divided by GM. So what is beta AC? Beta AC is the AC beta. So we know that beta, what is beta? Beta was IC by IB. So that was for the DC beta. So beta AC can be found from the AC current also. So let us take an example for finding the value of beta AC. So for that purpose, what we take, suppose I have a IB value, okay, and this IB value is having 1 plus 2 sine omega t, okay, and the unit is milliampere. And let us assume that the IC value is 100 plus 60 sine omega t, and this is also in milliampere. Now if I want to find the IB RMS value, hopefully you know how to find the RMS value. That is nothing but the DC square plus AC value divided by root 2 and whole square and whole root over. So what will be the value of IRMS? So DC value is 1, so that is 1 square. AC value is 2, so that means 2 by root 2 whole square and whole root over. So you will get the value of root over of 3 milliampere. Similarly, we will get IC RMS. IC RMS, what will be the value? Similarly, we can find that is 100 square plus 60 divided by root 2 whole square, this one. If you calculate this, you will find 112.96 milliampere. Okay, so we have got the values. Now we can say that the DC value if we find the DC value of the IB. So what will be the DC value of IB? That is equals to 1 milliampere. What is the DC value of IC? DC value of IC is 2 milliampere. Similarly, if we want to find the DC value, DC value is 100 milliampere here. So this is the 100 milliampere. 100 milliampere. Similarly, if we want to find the AC value of IB, so what will be the AC value of IB? So AC value of IB will be equals to 2 milliampere. 2 milliampere. Similarly, the AC value of IC will be equals to 60 milliampere. Okay, so beta DC will be equals to IC of DC value of IC and DC value of IB. So here is 100 divided by 1, so it is 100. So beta DC value is 100. But if we want to find the beta AC value, so what is beta AC value? So we'll take the AC value of IC, that's why I am writing small letter, so AC divided by AC value of IB. So it will be 60 divided by 2, that is 30. So this is how we can find the value of the beta AC and beta DC. Generally, in the examination, if the question comes from the beta AC and beta DC, you can see that the beta DC value and the beta AC value are provided and they are generally equals to each other. Okay, so if beta DC and beta AC value are same, so what will happen? So if the beta AC value and beta DC value are same, then what will be the value? So R pi value, what will be the R pi value? That is beta AC by GM, and beta AC is nothing but beta DC value GM, and beta DC, what is beta DC? Beta DC is equals to the DC current, collector current, DC base current, and IC by VT. So it will be equals to VT divided by IB. So if the beta AC and beta DC value are equal to each other, so we can say that the internal input impedance of the transistor according to the RE model, that is equals to R pi, so it will be provided by thermal voltage divided by the DC base current. This is a very important relationship, and this relationship is generally used in the case when the AC beta and the DC beta are same. So this is how we can find the input impedance of a bipolar junction transistor. Input impedance of a bipolar junction transistor. Now let us take the RE model that we have drawn here. So if we copy this, so let us copy this RE model. Okay, so let me copy this RE model into a new slide. And we'll use this RE model. We'll use this RE model. So this is the RE model that we have already seen. Now let us first denote the input impedance. Where is the input impedance? So if we want to talk about the input impedance of the bipolar junction transistor, so bipolar junction transistors, only for the bipolar junction transistor, this will be the input impedance. And let us denote it as Ri, because we have said that this is the internal input impedance of the bipolar junction transistor. Okay, so if we want to find the input impedance of the total circuit, so we have to take the input impedance from this point, and we have denoted this as Ri dash. Similarly, if we talk about the output impedance of the BJT, so output impedance of the BJT will be here, and the output impedance of the total circuit can be calculated from this point R0. So now this is the model right now, and we have to find the different values. So first of all, if we want to calculate the R pi value, R pi value means beta AC divided by the GM value, and we also know that GM into V pi, GM into V pi, this value, if I want to put the values, so GM, from this we can calculate the value of GM. So now from here we can say that this will be GM multiplied by this V pi value can be written as, what is V pi? V pi is nothing but the current into the R pi resistance, because the voltage drop across the R pi resistance. And what is the voltage drop across the R pi resistance? That is the IB into R pi. So IB into R pi. So from this, GM into R pi, GM into R pi is beta AC. So from this we can say that GM into V pi is equals to beta AC into the IB current. So that means GM into V pi can be replaced by beta into IB, beta into IB. So that means this output circuit can be drawn like this. So if I want to draw this output circuit, so how the circuit will look like? The circuit will look like this. Only I am drawing the output circuit. So there is a dependent current source here, and that was GM into V pi, and GM into V pi is equals to beta AC into IB. So I am writing here beta AC into IB. With that, there is a R0 parallel to this. So this is the R0, and here this is the collector terminal, and here it is the emitter terminal. Now in between the collector and emitter there is a RC resistor, that is the collector resistor. This is the RC resistor, and with that there is a parallel resistor called RL. So here this is RL. Very, very simple method, just you have to follow the steps. So this is the output voltage right now. So this is the output voltage V0. Now we have already seen that the current flowing through the load resistance is I0, and here the current is IC. So now if we apply the nodal analysis in this circuit, so what will be the nodal analysis? So nodal analysis, it will be V0 divided by R0 plus V0 divided by RC plus V0 divided by RL plus beta into IB, that is equals to 0. So if we take common, so there is V0, and inside the bracket there will be 1 by R0, 1 by RC, 1 by RL, and here it will be minus beta into IB. Okay, so now this is the way by which we can find the value of V0. So what will be the value of V0 right now? So V0 will be equals to minus beta into IB divided by 1 by R0 plus 1 by collector resistance, 1 by load resistance. So this is how we can find the value of V0. So V0 can be found like this. Now, if you talk about the input circuit, what is the input circuit? This is the input circuit. So now we will take this input circuit and we will analyze the VI. So from this figure, from the input circuit figure, what you can see that the value of IB. What is IB here? IB is nothing but the voltage across the RPi divided by the RPi resistance. So we can write the base current IB is equals to the voltage across the RPi, that is V pi, divided by RPi. Now, from this equation, if I denote this part as the 1 by RL dash, then what is the equation? We can write it as V0 divided by RL dash is equals to minus beta into IB. Using this equation, I can write here ki V0 divided by RL dash. V0 divided by, from this equation, if I use this equation here, so V0 divided by RL dash will be equals to minus beta or IB. IB value is this one. So if I put the value V pi by R pi, so this value. Now VI, this V pi is nothing but the input voltage. V pi and VI is same. So that means we can say VI by R pi. So we can say that minus beta VI divided by R pi. If we take the VI in the left hand side, it will be equals to V0 divided by V pi will be equals to minus beta into RL dash divided by R pi. So this is nothing but the internal voltage gain of the transistor. Internal voltage gain, because this part is the transistor and you are finding V0 by Vi, which is nothing but the output voltage of the transistor itself divided by the input voltage of the transistor itself. So it is the internal voltage gain. So we are finding the AV. So AV is nothing but minus beta RL dash by R pi, and beta by R pi is nothing but the the transconductance. So that means AV will be equals to minus GM divided by RL dash. So this is one of the most important relationship that you have to find in the examination. They will ask you what is the voltage gain of the transistor itself in the case of common emitter mode with RE resistance. Similarly, you can also find the current gain. So current gain value, what will be the current gain value of the common emitter bipolar junction transistor? So we will denote it as AI. We have already denoted that, and that is nothing but the collector current divided by the base current, and the collector current is by base current is beta AC, and we are denoting it as only beta. If we want to find the input resistance of the bipolar junction transistor, that will be equals to Vi divided by the input volt current, and Vi is nothing but the V pi, and this is by IB. So V pi by IB, if I put the value of V pi value has already found. V pi is nothing but IB into R pi. So if you put the value of IB into R pi, so नीचे आपका R pi, so R pi will cancel out. You will get IB. In the denominator there was IB. I have mistaken it. So IB will not be here. So this is the R pi. So IB cancel out. So you will get R pi. So that's why we have denoted the R pi as the input resistance. And you can see here that actually this is an input resistance. And what is the voltage gain of the BJT? So we can also find it as voltage gain of bipolar junction transistor. So voltage gain of the bipolar junction transistor, it will be the current gain into the load resistance of the BJT, load resistance of BJT divided by the input resistance of the BJT. Input resistance of BJT. Hopefully you remember this formula. This is always used in the case of bipolar junction transistor, that is beta RL dash and R pi, and this will be nothing but we have already denoted it as minus GM into RL dash. So this is how we can calculate the value of the voltage gain. Similarly, if we want to calculate the output impedance, so let us first calculate the output impedance of the bipolar junction transistor. So output impedance is nothing but R0, and R0 is nothing but VDC by IDC at Vs equals to 0. We have already seen that in the previous lectures. And from the voltage divider law, if we want to find the V pi, so V pi will be equals to Vs into R pi divided by R pi plus Rs. So if Vs is 0, then V pi will be 0. That is Gm into V pi will be 0. So that means the R0 value will be similarly the small R0 value. So this is how you can find the output impedance of the circuit. So output impedance of the circuit, you have find it using this. So now similarly the same thing can be done in the case of common emitter with RE amplifier. So common emitter with RE. So common emitter with RE means the circuit will look like this. This is the emitter, this is collector, this is base. So here there will be a emitter resistance and the name is RE. In the collector there will be a RC resistance and there will be a DC supply VCC, and in the base there will be a source resistance RS, and with that in series there will be a VS. So this is the VS source, and the output will be taken from this point, and there will be a load impedance here. So this is the RL and this is V0. Okay. Now hopefully you can draw the circuit of the RE model. Okay. So what will be the RE model right now? So if I want to find the RE model of this circuit, so the circuit will look like this. So this is base, this is emitter. Okay. So this is base, this is emitter. Now in between base and emitter, hopefully you remember there was a R pi resistance. So there was a R pi resistance. Then here there was a dependent current source. So this is the dependent current source, that is Gm into V pi. So that will be equals to beta into IB, or there will be a parallel R0 resistance. So here this is the collector, this is the emitter, and emitter is grounded through the RE resistance. So this is the RE right now. Similarly, if we go for this connection external elements. So RS, here it is VS, and it will be grounded here. Okay. Similarly, if I want to calculate RL here, so R, there in the collector there will be RC, and it will be grounded in the other end. So there is RC, and here there is RL. Here is RL. Okay. So this is the output voltage here. So here this is the output voltage V0. So hopefully you can find the any type of RE model for any circuits. If I ask you what is the voltage, input voltage across the R pi, anybody can say, sir, it will be V pi. What is the input current? Sir, IB is the input current. What is the output current here? Sir, IC is the output current. What is the load current here? Sir, I0 is the load current. What is the current flowing through RE? From this end, IB is coming, and from this end, IC is coming. So that means it will be IC plus IB. Okay. So this is my IE current that is flowing through the emitter. So this is how we can find the RE model of any circuit. Any circuit के लिए we can find the RE model. Hopefully you can understand what is the RE model right now. So what we have seen that using the RE model, if you find the current gain, of the previous circuit, you can find, I'm just writing the values, you can already find that just by some manipulation or mathematical calculation, you can find the current gain as minus beta. If you find the input resistance, it will be R pi plus 1 plus beta into RE. Next, if you find the voltage gain, it will be minus RL dash divided by RE. And if you find the output resistance, it will be the infinite. So this is how you can find the 4 internal parameters of the bipolar junction transistor in the case of common emitter mode with emitter resistance. So this is how we can use the RE model. And if you remember the values of these parameters in the case of without emitter resistance, so what was the value? So without emitter resistance, we are getting that the current gain was minus beta. Okay. RI was R pi. There is an extra term here for the case of emitter resistance. Next, the voltage gain. Voltage gain was minus beta into RL dash divided by R pi. And what was R0? R0 was small r0 like this. So this one is for without emitter resistance, and this is for with emitter resistance. Okay, so now you can see the difference between the emitter resistance and the emitter resistance where the circuit is not emitter resistance. First of all, for the semester examination, you have to understand these 4 parameters. You have to understand these 4 parameters: R pi, V pi, GM, and R0. And you have to calculate these internal parameters for the individual circuits: Ri, R0, voltage gain, current gain. And you have to calculate the input impedance for the total circuits, output impedance for the total circuits, voltage gain for the total circuit, current gain of the total circuit. So this row belongs to the input impedance, output impedance, and the voltage gain and the current gain of the individual BJT only. But this row belongs to the total circuits. It includes the bipolar junction transistor as well as the external circuits that we have connected with the bipolar junction transistors. So they are giving the values for the total circuits, and this is giving the value for only transistors, only bipolar junction transistor. So, and by some numerical methods, we have calculated the value of V0, we have calculated the value of the voltage gain, we have calculated the value of the current gain, we have calculated the value of input impedance and the output impedance. So this is all the methods are known to you. Srif only this portion has been changed. Only this portion has been changed, because in the hybrid parameter model we are not using this model. Right now we are using this model, and this is the most generalized model that is right now used for modeling the transistors in the AC domain. Okay, so this is how we are modeling. So this is all about the RE model. This is all about the RE model for the semester purpose, and we will see more topics in the upcoming lectures. So I'm ending the session here. So thank you everyone.